Professor Pinak Mahanta 10 years now, when we were doing some research projects together on rural biogas systems. And I was last in your part of India just a couple of years ago, visiting some sites, and I've got a few slides of that when I was actually visited a former student over in Nagaland. We were talking about some collaboration opportunities. So I'd like to again thank everyone for attending. I'd like to thank the organisers for putting on this what looks like a very interesting course, and for giving me the opportunity to speak to you today from the United Kingdom, where it's just after 9 o'clock in the morning. And it's also very cold here, so I'm missing the warmth of where you are as well. So, okay, so without further ado, let us begin. Okay, so I'm going to give a very brief couple of slides about Loughborough University. Then I'm going to sort of introduce the rationale for undertaking this presentation. I'll give you an introduction to the different examples of treatments for dealing with wastes, and then look at the methods, the life cycle assessment and methods which have been used, and the validation of these, and also some sensitivity analysis around those in terms of the actual results. So this slide shows you some of the campus of Loughborough University in the left. So it's pretty much Loughborough is a university town. It's about 1/3 of the population are students, and so that just gives you an overview of the campus. There's a map of Britain in the right-hand corner there, and you can hopefully see in very big letters in the middle there. I'll put the pointer on, laser pointer. So this is where we are. London is down here, and so it's about by the fast train, it takes about 1 hour and 10 minutes to get to London. And this rather sort of imposing but uninspiring building in the top right-hand corner, this is where I work most of the time. I'm at home now with COVID, but this is where CREST is based, in this, what is our Science and Enterprise Park at the campus. And there's a lot of companies and academic work going on in energy in this particular building. Okay, so I'm based at what's known as CREST, which is the Centre for Renewable Energy Systems Technology, which has been going for about 30 years now. And we undertake research, development and teaching in renewable energy generation, distribution and storage. And just to show the breadth of the work we do, we're about 15 academics in the staff. We've got maybe around about 20 RAs and 30 PhD students. So around about 65 people to 70 people in the group. And these are our research topics on solar materials, applied photovoltaics, wind energy, renewable energy for development, which is my area of interest, energy storage I'm also interested in as well, networks, and then multi-scale energy systems. So this is some of the work which I get involved in, and I suppose the interesting picture in the middle here, this is from, we did our research project with biogas with Professor Mahanta, who's pictured here. And this was a few years ago when we were looking at some biogas systems in Assam. This is not too far from Guwahati, and we were looking at a new fixed dome biogas installation here. And so that's just to say some ideas of things we do. This is where the ideas around municipal solid waste to energy has been looked at, and this is a gasifier from one of my PhD students. This is actually situated in Ecuador, so we had some research links in South America, so they had a gasifier here, and this was also being to make the syngas process. And I've also more recently been involved in work around microgrid activities. So in the top right-hand corner here, we've got a map of north of Borneo in part of Malaysia, and this was to do with school mini grids. And so that's, again, just to give a flavour of some of of my research interests. Okay, so let's get back to the topic now, and the motivation behind why it's important to look at waste. In terms of a bioenergy resource, it's material which has got energy value within it, and the reasons why we need to treat this. And obviously, there's more people. We have growing population. People are generally getting, general trends are that people are getting better off. More people are wanting to buy more stuff and use more stuff, and therefore we have large amounts of waste, and we expect that waste to increase to large amounts around the world. So this is the reason. The waste has to be treated somehow. And I'm sure you're aware of some environmental problems of water contamination, land contamination, and the oceans filling up with plastics. And so these are some of the motivations. So we've got that, and we've also got to deal with issues around global warming and other environmental problems. So the challenge really is to how do we treat this waste and manage this waste in a way. So, and of course, there are lots of different options here. You can look to produce recycle materials, actually recycle wastes, or you can convert it to energy. So there's lots of different routes which could be taken. We should ultimately try to recover materials as best as we can and reuse them, but we can't do that for everything. So this lecture, this talk today, is about how we manage the waste and how we can get the most sort of benefits from it. So municipal solid waste, again, it's basically everything we throw away, and in the UK we throw roughly about half a ton of waste per person away. It varies around the world. In some parts of the world it's much higher, in other parts of the world it's much lower. But the trend is as countries develop, more waste gets produced, and so we have this problem, and we have to deal with it. And again, it's made up of lots of different materials. Some of these are useful from an energy perspective. Some of them, it'd be much better to recover the wastes themselves. So if you can recover electronic wastes, recover metals and glass as well, and plastics, we can recycle them. But then there's the organic matter, which we could convert that into energy. And actually, plastics do have a high energy content as well. Although once burnt, then that's the end of their usefulness for that. So I'm going to look today at processes which are already technology ready. They're actually processes which could be used. I'm not talking about things which might happen in the future. These are processes which are already at demonstration stage, or also already at commercial stage. So, so this first graph here shows the sort of waste we're producing in the UK. So it's around about 32 million tonnes, which is roughly about half. We've got a population of about 65 million in the UK. So I say it's about half a tonne per person. And the trend has been that we're actually already starting to produce energy from this. So we are converting roughly 1/3 of this this waste to energy already. And we're also at the same time reducing the amount which is going into landfill, and it's a requirement that we can't put waste into landfill anymore because of the methane issues associated with uncontrolled landfill. And that trend is going to continue, and we should actually be getting to a point that we've got an ultimate objective within, well, when we were part of the European Union, I hope it still will carry on, that we will reduce our landfill to zero. But it's getting more challenging. It's getting more challenging to deal with waste in this way, because for us, people are concerned about energy to waste systems, and do they lock you into producing waste? Around Europe, converting municipal solid waste to energy is quite a major activity, and particularly again in the more developed countries. So, for example, in the UK, we've got about 41 plants which are converting waste to energy. In France, they've got 126 plants. Germany, 121 plants. Italy, 40 plants. Sweden, 33 plants. And bear in mind that Sweden's got quite a low population compared to the UK. It's really converting nearly 80% of its waste in Sweden now goes to energy. So we've got, you can see that, these are, mature technologies, but they tend to be, the most mature ones operating tend to be basically incineration plants. We call them energy from waste, or we call them, energy recovery facilities to hide the fact that they are largely incinerators, which do combustion. But as I say, there are other routes which could be taken, and technologically they're developed, but it more comes down to the economics. Are they economically mature technologies? The Netherlands as well. Again, a small country, but converting quite a lot of its waste to energy. So the objective then of this talk then is to compare different technologies to valorize, convert municipal solid waste, but using a systematic life cycle assessment approach. So there are 7 alternative technologies which are going to be looked at here, and this flow diagram shows us the routes which I'll be exploring in the next few minutes. So we'll start off then with the first route, and that is the mature technology. This is the thing which people go to as the route for treating waste. It's because it's the least complicated. It's the in terms of, I suppose, off-the-shelf systems, for want of another word, it's the cheapest option for that, and produces electricity. So basically, you have municipal solid waste, you combust it, and you produce steam, and then you make electricity. Okay, that's the sort of the simple approach. The second, I suppose, closest to commercial routes is gasification. And so this is gasification where you're producing gas, and then from that gas gets combusted, heat, steam, and to electricity. The advantage with gasification is that you can keep that gas to a time when you might want to use it. So it's possible to store that gas, and that has advantages in terms of generation, because with combustion you have to use that electricity when it's being burnt, and instantaneously. And with gasification technologies, and also the other technologies as well here, you're producing products which you can use at a more appropriate time. So, for example, if you have you think about, I don't know how much you're aware of the sort of the electrical profiles, but normally there are peaks in electricity use at particular times of the day, especially in the evening. So if you produce your gas at one time of the day, you can store it for a short period of time and then use it in the evenings when the peak demand is available. And financially, that has advantages for companies, because at the peak times, electricity is usually more expensive, and so you can then make more revenue from it. And that's that's sort of the ideal situation. Okay, so coming back to the processes, then we've got a route in which we then produce from the syngas we produce methanol. Okay, so again I'll show a little bit more detail about these processes in a few minutes. We've then got a route to produce from methanol dimethyl ether. Dimethyl ether is a diesel-like compound, so it can be used as a replacement fuel, and it can also be used for other chemical industries. So again, you can think about what the particular value is for those for these chemicals. Now, this is what's termed the indirect route, so you're actually making syngas through methanol to dimethyl ether. There's also another route, which is going directly from syngas to dimethyl ether. We've then got the route which is methanation, so actually turning the syngas into methane as part of, again, a chemical process. Okay. And then the seventh route is using that syngas from the gasification program process and making electricity from fuel cells. So those are the 7 routes which I'll talk a little bit more detail about now, before we then look at the life cycle assessment of these routes. So it's pretty much top level stuff. I'm not going to get into a lot of the detail of the process engineering, but really just to give you an indication of these different technologies. Okay, so you can see that there's, from these different routes you can produce a range of different outcomes. You can produce electricities, gases, or even chemicals for industry. Okay. So this is the first route then. So as I already explained a little bit already, this is just the combustion processes. We take the fuel, which comes in through this feed, gets fed into the boiler system, and as it combusts, it produces heat, which then goes off to the boiler, and that then can be used to generate steam. You get some waste from this as well, from this activity. So what we call the sort of the slag material, and this could be material which you could actually recover metals from. So you can get your metals back from this process, which has some economic value. And the material can also be used as aggregates for building materials. So that's again it's the sort of the basic process. So just a couple of pictures here just to illustrate what goes on in terms of the processes. The principal output from this is electricity, and that's what we're looking at in this process. Gasification, as the name says, it's about making gas, and there's an example here of a type of gasifying system. There are different stages from when your waste comes in. It goes through drying, pyrolysis, reduction, and oxidation, and you get some, again, ash being produced from this, and that is then used. Again, you can recover materials from this. And so the driving reason for this is to produce this gas, which then can be used at different times. There are lots of different chemical reactions taking place here in the different zones. So we're producing carbon monoxide, carbon dioxide, hydrogen, water, and methane in varying amounts. So this is sort of the reason to produce the gas. And from this gas, we can then generate electricity, potentially at a time when we want to make use of it. And then also we can get some residues as well, which we can then utilize for the future for other purposes. So recover materials, maybe make this waste as building materials as well. And at this point, I just wanted to start talk a little bit about one gasification plant I visited a couple of years ago, which is not in Assam, just to sort of show a little bit more about the process. And this is where I visited one of my former students. They make about 80 tons of biscuits per day at this factory. This is in Assam state. And it's just to illustrate the gasification process in more detail, because most of the well, in fact, all the other technologies which we're going to be talking about rely on syngas to start off with, and that comes from gasification. So all the processes, the other 5 processes plus gasification, are relying on gasification. So that's why I wanted to spend just a few minutes looking a little bit more detail about gasification. So this is a very interesting facility because you've got this biscuit factory, and it's being the heat for this factory to make the biscuits is actually being derived from biomass rather than waste. They are getting bamboo from local farmers, which is they use a local agent to get the bamboo from the farmers. It then gets fed up into the from this stockpile. It then gets hauled up on this lift into the top of the gasifier, and these are the gasifiers here. After the gasification process, you go through a whole range of cleanup processes. So there's a scrubbing of the gas to get rid of particulates and to get rid of compounds, acidic compounds, to neutralize those which may be being produced. And also cooling stages as well. So you've got scrubbing, dry scrubbing, wet scrubbing, acid neutralizing with activated carbon as well. And also cleanup to ensure that you're getting as good quality gas coming into the factory, because it's a food processing factory. And also the effluents from the process of water is also cleaned up. But the one problem though with gasification, and it's really something which would be needs still research, is how to actually fix the tar problem with gasification. So on the left-hand image here, this is the tar cleaning up process. But even after the gas has been cleaned up, going through a factory, they still have tar traps which actually capture the tar to ensure that it's not getting contaminating the food. So that's just I think a very important research topic, which seems to be still problematic in gasification technology. I'm not sure whether we'll ever get that fixed, but at least what they were telling us at the factory is that tar has an economic value and is actually used to repair the roads in the area. So there's still some benefit with tar. Okay, so let's now go back and consider the different processes then. So this is just to, again, I'm just illustrating the different processes. So this is about methanol synthesis, where you have your gas coming in here at the top, and then you have your catalysts and reaction chamber, and also this then allows you to then produce your mixture of methanol, but also some gas will come out which hasn't been reacted, and the heat generated in the process can then go off to boiler water and be used for electricity generation. And these are the main the simple reactions of taking carbon monoxide and carbon dioxide and hydrogen from the syngas and converting that to methanol, and you get water as well, which can be used for steam generation. And the products from this process are the methanol, the fuel, plus electricity. So those are the main products that we have. Then the dimethyl ether, which is our diesel substitute, or our chemical processing compound. So again, we go through a stage of taking in the gases to produce methanol, which then gets further converted to the dimethyl ether. And again, this is through use of metal catalysts, and produces a fuel, and also electricity gets produced as well. And I'll talk a little bit more about the volumes when I move on to the life cycle assessment stage. Then we've got our solid oxide fuel cell route, and so this is where again we're taking the syngas compounds coming here, so the carbon monoxide, methane, and hydrogen, and they then through the fuel cell react with oxygen and give us water, some carbon dioxide, and unreacted hydrogen and carbon dioxide, and this then generates electricity. So the primary product from this is also electricity, but again it's electricity which could be generated at times when you need it. So if you've stored your gas, you can then use your electricity. And then the an advantage with using fuel cells to generate electricity rather than just burning the gas is that you're not wasting heat here, so you're not really generating heat, and you will get more electricity being produced. And then methanation, I think this is the last one. Yeah, so and here we're taking our syngas and we go through again a reaction process with catalysts, and we produce methane as part of this. So if you want to use methane, pure methane, which could then be used in engines, gas engine use as well. Again, my purpose is not really to explain a lot of detail about the chemical processes. It's more about how we compare these processes from the life cycle assessment approaches. So again, these are our reactions to produce methane. And carbon dioxide given with hydrogen given as methane and water. Those are our products. Okay. So let's look then now at the some of the methods where we're looking at for the life cycle assessment approaches. So life cycle assessment is a means of trying to look at industrial processes. So it's not about planning or building systems, as it's actually looking at processes which are operating. And the idea is to think about, well, okay, if you're a company, how can you improve your processes, and also think, why would you want to improve your processes? Well, it comes down to resource efficiency. We are in a finite world. There are only so many resources available to us, and we shouldn't be wasting them. And if we can reduce our waste from an industrial perspective, hopefully that will mean you reduce your costs in terms of materials you use. By doing that, then your profits will improve. And then if you're a big company, then it makes your shareholders very happy. And it also allows you to give yourself a badge. And this is ISO 14400. So you can actually have your processes being assured and approved through the ISO 14040 process route, which for life cycle assessment. You can think of this as a really good way of getting industry to really think about what their impacts are and how they can improve their industrial activities and reduce their environmental footprint. Because there could be processes which are harmful to the environment, but they could also be processes which may be actually harmful to human health. And so we can then think about how we can reduce that. Now, life cycle assessment is an established process. There are some very good tools available to use that, and there are handbooks about how you do this work. So it's well established, and it's, I don't know if you heard of the ISO 9000 series, which is the management, just for business management. It's a very similar route to that. So rather than being a business management process, it's actually an environmental management process, an environmental management system for your industry. And it's made up of 4 stages, which are shown here on the right-hand side. You've got your overall goal. What is the purpose? Why are you doing this? What is it do you want to improve? And the purpose also introduces a systems boundaries, because you could go from the very origins of your product. So, for example, you can look at the resource extraction of your products, what you actually want to make. You can also consider what happens to it at the end of life as well. But you have to decide what the system boundaries are going to be. And often it's about the process. This is where people will see the process. So actually taking in your raw products and actually ending with your product going to market. And that's the most typical system boundary. So I've got this red dotted line around here to show the manufacturing process. But you could go further. You could look at the whole embodied energy, embodied carbon process, from actually digging up your materials from the ground, and then what actually happens to them at the very end of their life. Now, in waste to energy processes, we're actually dealing with products which are at this stage, this end of life stage. It's the stuff which we've thrown away. That's what we're dealing with, and so we can't really look at the whole process before that. So we can only really concentrate on this particular phase. Okay, so you need to think about what your system boundaries are. And there's also a term of functional unit, and this is actually how you try to standardize your process. So so it could be, if you say a car manufacturer, say, well, how much material do we use to make 1,000 cars? Or if it's food processing, how much do we need to make 100 tons of biscuits, for example. But you need to sort of standardize so you can then compare your processes with other processes. So in this case, we're going to look at a mass of waste, municipal solid waste. Okay. The second stage is the inventory analysis, and this is really looking at all the inputs and outputs in the process. So how much energy is coming into the process, what materials are being used, and what are the outputs of your processes. So are there any intermediary products which are being produced, and are there any wastes being produced? So you need to look at your process, and that requires data collection. So you then have to get data. So you're needing to go to your records to find out how much material you're using in your processes. So, how much energy is being used, where's that coming from? If you're using water, how much of that is being used, and where does that go within the plant, and what happens to it? So, so that's running across the process, and then you need to think about what are the environmental effects of these. So, what does that actually do? So where are the burdens? Is it an effect on human health? Is it an effect on the aquatic environment? Does it cause global warming? So those are the sort of aspects which we would look at. And that would then lead to an assessment. And this is where some of the tools come in, is actually how you take measures of the impacts, of how much of an impact is that going to be. So you look at different categories and you estimate to the best as you can. There's a lot of databases available to help. There are lots of tools now which can enable you to quantify what those effects are going to be. But ultimately, it comes down to interpretation. Okay, so what does it actually mean to the business? What does it actually mean to wider society? What sort of decision will you make about this? Will you improve your process? Will you try to work out what it's going to cost to improve your process? And this is where you look at the significant issues, because you could look at everything, but some of these maybe maybe a tiny amount of compound gets produced, which is very benign, and you don't need to worry about it. So you need to concentrate really on the significant effects and evaluation of what this actually means. So again, looking at what standards there are. So if you're producing wastes or gases which are breaching standards, maybe you need to then think about how to reduce those and reduce your environmental harm. And so you have to do this evaluation process to actually work out. So that's where experts would come in and help companies, or companies may be big enough to have their own environmental management teams as well. And in the waste to energy sector, because it's sometimes seen as controversial and deals with polluting compounds, then there will be usually environmental officers associated with the industry. And then you come to conclusions about what is it you're going to do. So that's very much a summary of the life cycle assessment process. And so we'll look a little more detail about this. So I'm taking UK waste composition as an example here. This is a sort of the nature of a typical UK waste. It varies. It varies where you are in the country. Depends on, for example, if you're in a very affluent part of the country, you might find you're producing more waste than from areas which are more deprived. It also varies seasonally as well. So at different times of the year, waste will changes. Our diet changes. For example, we eat more salad in the summer in Britain. We tend to eat heavy foods, lots of carbohydrates in the winter. So the mixture of foods also and materials changes, and particularly times of year, you get a lot of waste at Christmas. So you find that the waste will vary, and it varies around the world. If I did this in a different country, you might find, say, for example, when we were doing work in Ecuador, that the organic compound, organic makeup was about 70% of the waste, because there's less plastic and also less, I suppose, less developed, and therefore less material has been thrown away. So it's very much varies around the world. You might find in India you'd have a different. If we did this research in India, we might find we have a different mix of organic wastes in our waste streams. Okay. Now, the functional unit for this this topic today, this research, is 1 ton, 1,000 kilograms of waste. Okay, so what we're looking at. So in every example here, for every 1,000 kilograms of waste, we will produce certain amounts of electricity and chemical compounds and gases, and we'll also use a range of different materials as well. Okay, so I'm now going to look at the overall processes for the different routes here. And so this is the combustion route. And so if we take a ton, 1,000 kilograms of ton, we need some air for this. We need some urea to help with the combustion processes. We may use methane as well to actually get the combustion process started, because we can't to get to temperatures to start off with. We'll then hope to produce around about 428 kilowatt hours of electricity. So again, and these figures come from literature. They also come from the modelling work which was undertaken to produce this. So these figures have been validated against other literature. And we also then have materials to do with the treatment of this waste. So again, thinking about the gasification slides I showed, we've got to do air pollution control. So to neutralize compounds such as acidic compounds, we use lime. And if we get things such as dioxins and furans being produced, activated carbon to capture those. So ultimately what goes up the flue gas will be nitrogen, carbon dioxide, water, maybe a little bit of oxygen will being released. So we're getting there from this process about 428 kilowatt hours of electricity. In gasification, so again, and this is just one example here, we're looking again of in the 1,000 kilograms, we're producing the slag materials. We've got some metals. We're also producing electricity, but we've also got to do with the cleanup. The electricity is a little bit lower than through combustion, but again, from an economic point of view, it could be more advantageous to use gasification. Then if we consider the methanol process, again, we can see we've got a range of different inputs here, different compounds being required for producing the methanol. So firstly, we're treating the syngas to ensure that it is doesn't contain compounds which would potentially damage the methanol production process. We have a distillation process, and then we also have methanol being produced, and then unreacted gas will produce again some electricity from this. So you can see again, in terms of the process engineering, we can see the inputs and outputs taking place. But overall, we get some methanol being produced, and we also get some electricity. And methanol, again, these are being produced because of their value, and also and the energy density also with methanol is also quite high as well. So it's useful for fuel for vehicles. We've then got the indirect dimethyl ether synthesis process. Again, we can see we've got the treatment here again of the gas. We're making methanol here, treating this, and then from the methanol we then make our dimethyl ether. So we're producing about 60 kilograms of this, but the unreacted gas is the same. So again, we're able to produce about 230 kilowatt hours of electricity. For our fifth process, then this is the direct route, and so rather than going through the methanol process, we're actually going from the syngas. So we're treating the syngas. We're then producing dimethyl ether. We then produce the DME at about 69 kilograms, and then we're also producing some electricity. So we produce a little bit more fuel and a little bit less electricity here. Then with the solid oxide fuel cells, so again the gas from gasification. It doesn't need so much cleaning up as the methanol and dimethyl ether processing. We then get conditioned syngas, which then produces 711 kilowatt hours of electricity, so we're producing more electricity, we don't have thermal losses. And then if it's unreacted gases can then go into a more conventional steam generation route, could also give us another 181 kilowatt hours of electricity. So we can produce a lot of electricity through the solid oxide fuel cell route. And then finally, the methanation process, and this again goes through cleanup, yields us pure methane gas, which can go off to a bottle gas and produces some electricity as well. So those are the main processes, very briefly to look at these. And so now we'll then consider what we then do in terms of impact assessment. Okay, so what you would do is once you've got your what we call this our life cycle inventory. This is our life cycle inventory of inputs and outputs. This is what we're looking for here. What we would do is take our life cycle inventory results, and we would then take the numbers and we'd then use methodology called Impact 2002, which enables us to then look at what are the effects going to be at different stages. So rather than seeing what the overall effect is, it allows us to say, well, what are the effects going to be in different aspects of impact on people, society, the environment, the climate, and then resources. So it allows us to then think about what of these compounds are any of these carcinogenic? Are compounds, are they going to affect people's cancer? Are they going to affect respiratory health? So the inorganic compounds, are any of these radioactive? Will any of them cause ozone depletion, which could then affect getting more ultraviolet radiation, and that affects our health then as well? We can also look at the effects on the water environment, so in terms of the aquatic chemical pollution, terrestrial pollution, the effects on nutrients on land and water, land area, and then also things to do, are we going to acidify the water, or are we going to cause the eutrophication, so actually causing enrichment of the water, global warming, and then the use of non-renewable energy, so fossil fuels, and also what minerals we use. So we look at what we had previously, the inventory, the process engineering, and when we can run this through, take those numbers and run them through to see what those effects are going to be. And then this will then allow us to then think about, well, what is the overall impact and at the endpoint categories on human health, the ecotoxicology of the processes, climate change, and resources. And so that's really what the driving reasons behind life assessment are to see where the effects are going to be and what the ultimate consequences are going to be. So let's consider then some of the results of these 7 processes. So this is the overall comparison of the processes. Now I apologize because I changed template to go to a university template. The coloration on the right hand side here doesn't match the charts, and I'm not skilled enough with Excel or PowerPoint to sort that out. I do apologize. But basically, we're going 1, 2, 3, 4, 5, 6, 7. So we're going from left to right. So we've got the combustion is the left-hand one, and methanation is the right-hand one. So if we look at this top chart here, and this shows us the effects on human health, ecosystem quality, climate change, and resources for these waste-to-energy processes, and the difference, for the different processes. So for human health, we can see, well, the best one I think it looks like is gasification. So in terms of the overall processes, gasification appears to be the most benefit to minimizing impacts on human health. That's what's shown here. In terms of the effects on the ecosystems, there tends to be a great deal of effect across the processes, and you can see here again, in all the areas, the sort of ecosystem areas, there's not a great deal of effect. In fact, the methanation process does seem to be the one which actually would be the least harmful or has some impact or benefits to the ecosystem quality. For climate change, there's not a great deal of difference, except that gasification does seem to stand out quite a bit. The others are fairly standard, because, I guess because gasification is making more methane. But in terms of overall, for climate change, solid oxide fuel cells would appear to be the ones which are having the least impact on the environment. And then for in terms of resources, so fossil fuel resources and mineral resources, then again, not a huge deal of difference between some of the processes, but the DME, the direct DME, is the one which comes out the best there. So this gives us, normalized across all the categories, and it would then come down to decision making about which ones you'd want to say are going to be the most important to you. And also then come on a little bit more to look at the sensitivities. But moving across the midpoints, and again, this is where you get into more detail. You can see that actually, generally, there's not too many effects on human health, except in respiratory areas. So actually, because you're going to potentially producing particulates, you're potentially going to be producing gases which may irritate the lungs. And so those are the areas which are, potentially the areas of concern. So there's not a lot in the general natural environment going on. But then in terms of global warming, we can see that obviously we're going to be producing carbon dioxide and methane in some cases, which have high global warming potential. Okay. But the advantage though is that because we are not, we're dealing with waste materials, and actually in terms of generating electricity from waste, we're actually making use of these wastes to make electricity. We're not having to get new materials, new biomass, or coal or oil to actually generate the fuels and the electricity. So from a non-renewable energy perspective, then all of them do seem to be beneficial from that point of view. But yeah, we're looking at a bit more detail about these now. Okay. So again, apologies for the coloration, but at least I've got some notes here to show you where the effects are. So overall, for combustion results, it's the emissions are the problem, are the cost. Okay, but we also have some avoided burden as well. So as you can see, we've got above and below the line here, and so we're actually getting emissions, yes, which are an environmental burden. We're also getting a reducing of some burden by the electricity which they're generating. So that's where the benefit comes for these processes. So actually reducing that, and particularly the resources overall, is a way to reduce environmental burden. For gasification, it's similar. We're getting emissions from the carbon, from the gases, from carbon dioxide, methane, but we're also getting the benefit of electricity as well. We can recover some. This shows a bit more. We can recover some minerals and metals as well. For the life cycle assessment of the methanol process, again, it comes down to, it's the emissions of the issue, but we've got benefits of electricity and also benefits by making the methanol which is being required. So we're trying to see what the balances are between the burdens and the benefits of these processes. For indirect DME, again, it's pretty much similar. So emissions are the cost, and the benefit is the electricity and the fuel, the diesel substitute. Similar for the direct DME process as well, emissions, then we've got the electricity costs, and then we've also got your DME being produced. For the solid oxide fuel cells, again, we have emissions as well from this, but we've got much more electricity being produced, which is a much greater reduction in this environmental burden, climate emissions, by the fact you're generating so much more electricity with solid oxide fuel cells from waste than the other processes. And then the methanization process, then again, we're getting emissions, We don't generate a lot of electricity here in methanation, but we do produce the gas as well, which is the benefit for this. And again, you can see across the main routes, but also, again, it's a very similar pattern also with the endpoints and the midpoints as well. So to summarize this overall, then if we actually look at them at their endpoint, this is the ranking. Again, it's been normalized to give us the different processes, and we can see here that, as we showed a bit earlier, in the top, or the best for each of the processes is the human health gasification, ecosystems is methanation, solid oxide fuel cells is global warming potential, and the overall the resources is our best for that. Okay. We can also see what ranks second. So for gasification, it's good. It's also pretty good in terms of ecosystem quality. But actually, overall, though, there's not a lot really wrong with the ecosystem quality overall. There's not a lot of difference between these. Methanation is good for ecosystem and global warming potential, and then global warming potential and resource. We've got direct DME synthesis and solid oxide fuel cell. But overall, we can probably see that solid oxide fuel cell seem to rank pretty well across all of the areas, and and this would appear to be, from a life cycle assessment point of view, way to go forwards for treating waste, because you are minimising your global warming potential, and also it's also good in terms of its overall effects, low effects of human health and resource consumption as well. And the ecosystem doesn't have, there's not a lot of difference across all of the areas there, so it doesn't make a lot of difference. But it's not the technology of choice, because it's still, whilst technologically it's developed, it comes down to economics, and that combustion is really the one which people are using because it's cheapest for route to go. But it would very much depend on how you can actually make solid oxide fuel cell technology to this scale to actually be able to use it rather than with combustion. Because combustion, it's wasteful because you have a lot of heat wasted, whereas with the solid oxide fuel cell, you're generating a lot more electricity from it. But that comes down to areas outside this topic today, which is the economics and the business models which are required, and how you'd actually decide on tariffs and to do this, and also valuing. I think also we aren't really valuing the cost of carbon dioxide. What should a ton of carbon dioxide cost? That's again, that gets into another topic completely. But what we could also do is to think about is, okay, well, are all these processes optimized enough, and are there things we can actually do? And there are developments taking place in the production of methanol and dimethyl ether, where we're actually now looking at being able to get more of the product being produced by making the processes more efficient. Generally, the conversion rates are, as you can see, there's a lot of unconverted gas. So if you remember from the slides earlier, there's a lot of gas not being made into methanol or dimethyl ether, and that allows you then to generate electricity. So is it possible to produce more of a product? Because the methanol and the DME as fuels have got a high economic value. So if we can improve those chemical processes, then can we then change this overall life cycle assessment? Because if you're getting more fuel, that could change our numbers. And so there is research going on, some of it at Loughborough, to look into ways to improve the processing. Okay. And experimentally, we can see that we can improve the yield from about 0.4. Okay, so in terms of the overall model, of methanol production, the yield of, so this is the conversion of methanol of gas of a syngas to methanol and DME, it's round about 0.4. So that means about 0.6 is unreacted. So you're getting gases unreacted. And so if we can do this, we can actually see, can we see some increases and changes in yields? So if we increase the yield, if it's possible, and again, an experiment it seems to be done, we can produce more methanol, dimethyl ether. In doing so, we then reduce the amount of electricity which is being produced. So we're making more dimethyl ether and less electricity, because that's what's going on here to increase the methanol DME productivity. So experimentally, this type of thing appears to work. Now, this will then have some impacts on the overall processes. So if we look here at the methanol, so if we look at the top figure here, this is the original global warming potential for the burdens and avoided burdens. So we're getting overall about 569 kilograms of carbon dioxide being produced. By increasing the yield of methanol, we then get this down to 525. So we're reducing our impact. Okay. Similarly, if we then are doing the same with indirect DME, we can see that we are able to go from 750 again. That's a total burden. 544 is the total overall, and then we can reduce this a bit as well with the indirect DME down to 488 kilograms of carbon dioxide being produced, and likewise with our third process, the direct DME, we can see that by increasing the yield of DME and all the other processes, we can then reduce some of the global warming potential of these processes, which again, it's a good thing to try to do. And it's to think about, the model which was developed for these processes as well, are helping in the overall validation. And what this then does is, again, you can't really show here, but we've got our values at the top here, and we can see, sorry, shifted a little bit, I'm afraid, but we actually can see we get some reduction in the areas of around human health. So we see some improvement in human health here, and we see some reduction in climate change, and we see some marginal reduction in resources here. To show you that, overall, if you're looking at the sensitivity of the model, we can reduce the overall impacts on our life cycle assessment. So this could then, from a process point of view, you can see, well, actually, we can maybe modify our industrial processes to treat waste to reduce the impacts from those three processes. So this is where we were ranked at previously. So this is what we started off with. So this is where we've got the existing yields and the existing ranks of our categories for endpoints. And then if we then look at the overall effect this has on our life cycle assessment processes, so if we increase the yields of methanol and DME, we can see that the direct DME moves up some stages within the processes, so we can see how it shifts, and we see some other processes move down, so their ranking is reduced. So it would then appear that if you are able to modify the process, you can actually reduce your overall life cycle impacts associated, particularly with DME. It doesn't make any difference to the indirect, but it does mean that overall DME would appear to be the best in terms of its overall life cycle assessment by this looking at the sensitivity and changing the yield. Okay, so this is something which doesn't exist now. It's something which is new. The left-hand table, part of the table, is the existing systems with existing technologies which are ready and can be used in the market. Whereas on the right-hand side, with research, we could then potentially see some changes to this and improvements, making DME potentially a less environmentally harmful process. But as I say, ultimately, these things are going to come down to decisions about how much, what we actually want, what products do we want? Do you want these liquid fuels? Well, you know, we need liquid fuels which are not going to be coming from fossil fuels. That's very important. We've got to, when we're thinking about sort of the net zero future world, how do we get to 2050 with running without carbon from fossil fuels? Is that possible? So we need to think about research into alternative fuels. Batteries are going to be very useful for light vehicles, electric rickshaws, electric bikes, electric cars, but heavy lorries, big lorries, traveling long distances are still going to have to need the high density fuel to get them around. Okay, batteries just don't really cut it for high density of energy. Okay, so overall then we're looking at DME appearing to be the best process. Okay, so come to some conclusions now. Okay, so this methodology then undertaken, this life cycle assessment, looked at different ways of converting municipal solid waste into electricity and chemicals. And it was focusing on those technologies which have got this high technology readiness levels, so those which are at close to market. What it shows is that it's a complex process, that you have a whole range of different outputs from this, and depending on what the priorities are, you could potentially come up with different answers for your preferred routes. So there are lots of different objectives here in nature. So for example, if we're looking at human health, as I said, we maybe think that gasification would be the route to take. Considering ecosystems, and maybe it would be the methanation route. For climate change, solid oxide fuel cells. And then if we're looking at resources, there's the direct DME. But thinking about the charts, there's in some cases not a lot of difference between some of these amounts, particularly in terms of the different methanol and DME processes. And generally, global warming is quite similar, apart from gasification and the solid oxide fuel cells. The ranking, is helpful. But the difference between the numbers, in some cases, might be very fine. So whereas you're looking at difference between like 2, 3, and 4, well, actually differences may be very small between them. But it's but I think it's been hopefully a sort of an interesting way to look at these ways of treating waste. So overall, the solid oxide fuel cells as a technology, appears to be the best performance across the board. We looked at some sensitivity to see if we increased the amount of methanol and DME being produced, which did show reductions in electricity generation, but also they reduced the environmental impacts of those processes. And actually then DME ended up as being the best technology overall if you increased its yield. But I say this is moving into the experimental end of things. Beyond this, the economic aspects would really come in play here. So you'd be really looking at the economics of the different processes, different routes, and decisions, and where your costs are going to be. I think what's really important is to get from my perspective, a real true value of the environmental cost of carbon dioxide. There are schemes where you can offset your emissions. And you may pay $11 per ton to some farmer in Africa, so that they will then be doing something which doesn't produce carbon dioxide. But the real cost of carbon dioxide, it's at least an order of magnitude greater, $100 per ton. As we're getting closer towards sort of high levels, our emissions are going to sort of reach our global warming budgets. this price for carbon dioxide needs to rise. So it's certainly beyond the scope of this lecture to talk about this, but it's something which has to be considered, because if you're going for the lowest cost approach, which is combustion, you can see that it's not the most environmentally benign point of view. We don't really have scalable technologies for solid oxide fuel cells yet. The technology is ready, but it's not economically ready. So we've really got to find a true price for carbon dioxide, rather than sort of the low prices. You can go to a website called Gold Standard, and if you're a company, you can then go and pay to have your own carbon emissions offset for a fraction of the true cost. So that's really my final message. I think this is a useful approach to take in terms of trying to understand the environmental aspects of waste to energy schemes. It does enable you to do life cycle assessment, does allow this functional unit, this like-for-like comparison, so that you can compare and get valid results, and then also then you can sensitize this and see how by changing parts of the process you can then see whether you can reduce the overall environmental impacts. Okay, I'd like to finish by just acknowledging some other co-authors for this research. So Dr. Nuchapan and also Dr. Brahmin, the Ministry of Science and Technology at the Royal Thai Government in Thailand, and also Angavika Yaptomi, who arranged the visit a couple of years ago to the biscuit factory. And some of this work was presented at a conference just a couple of years ago on green process engineering. Okay. Thank you very much for your attention, and if there are questions, I'll be happy to take them.
Thank you, Dr. Richard. It was so extensive, elaborate research work that you have discussed with us. Thank you. And I hope the participants have got a lot of knowledge, and they have understood about various systematic life cycle assessment processes. So participant, if you have any question, we have Dr. Richard Blanchard from Loughborough University, UK. So you can grab the opportunities. Please ask anything that you want to ask regarding this topic.
This topic, yes.
Anybody? Well,
someone's raised a hand.
Yeah. So it looks like from a presentation that Germany is the leader so far as these processors are concerned. So are they using the same technology which you explained, or they have some improved versions of that?
Thank you very much for your question. Yes, it's certainly would say that it's the more advanced countries in Europe, in the west of Europe, who are looking at this, and so Germany really has been taking the lead. They have had some advanced gasification. They have moved into the advanced gasification route, as well as the combustion route as well. So those are the main two processes. They have looked into, there's a plant at a city called Karlsruhe in Germany, which has a combined, it's a waste to energy plant which has a combined pyrolysis gasification process, and they produce not only the gas for electricity and the chemical industries as well. Salts are also being recovered. So Germany has very much been a lead, because it's led a lot on the environmental legislation. So the greening of Germany is ahead of most other countries in Europe. But Germany itself is also, they are struggling with the amount of waste being produced and dealing with waste as well. So how to actually recycle as much as you possibly can. And I suppose Germany, Denmark, UK, we're getting 40, recycling rates now, maybe a bit higher, but it's getting much more difficult to get above that. I mean, there was a European legislation for 75% recycling, but it doesn't seem to be achievable, because it just becomes the cost of recovering material gets so high that you can't recycle, and that the only option really is energy from waste to deal with this, or we re-educate ourselves to not produce waste, which which then has economic consequences. So certainly Germany has been the lead from this. Sweden is also very much has a no landfill policy, and as I said, it's got a lower population, but it is already treating 80% of its waste is going into energy schemes now. Other European countries which are more developing, say for example in the southeast of Europe, then still landfill is the main activity. So places like Greece and Bulgaria, still they're doing a lot of landfilling. They haven't really got progressed waste recovery, energy recovery from waste yet. But it's something which has to be dealt with, because the methane effects of landfill sites is much greater because it's uncontrolled than if you've got plants which are able to either combust it or gasify it, where you can actually control where the gas goes. So Germany is certainly leading this area.
Thank you so much.
Okay, Avinash Behera is having some question for sir. Avinash, you can start. Avinash, can you hear me? Avinash? Well, before he asks something, Dr. Richard, I have one question that most of the researchers that I have interacted, some of them are working on gasification using biomass, and they complain of the production of tar during gasifications. So can you advise some convenient method or addition of some additives to reduce the formation of tar?
Yeah, that is the question of how to treat tar, and it's something which is it's problematic. I honestly don't have an answer to how to deal with this. It is a question which we're all trying to deal with. I mean, apart from if you can capture it better with tar traps, that's not a very good process as such. But it is that is one of the questions of we need the answer to, because getting tar into engines, it's just a terrible process. And even as you saw from the slide I showed you, that the biscuit factory, they're treating and trying to capture all the tar they possibly can, but still some gets through in the and still has to be trapped in the production line. So it's still it is still a problem which needs to be solved, and it's certainly an area where good research is required to try to reduce this. I honestly don't have an answer. It's something which I'd love to solve and love to work with people to solve. I think there probably are chemical routes which could be done for this, but it's how to stop it. It's really how to stop it forming. I suppose that's really where we want to try to do this, and it may be because it's the challenge of having temperature in a gasification at the right level to produce the gases you want, as opposed to if you had higher temperatures, then you wouldn't be getting you wouldn't be getting the gases you want, but you'd hopefully stop the formation of tar. in these reactions. So it's it's a real difficult question, and I'd love to know what the answer is and how we can employ it. When we had the project with Professor Mahanta, some of our colleagues at another university were working on gasification in rural areas, and it was Dr. Andrew Rowlinson. I mean, it was just tar was his bane of his life. That was ultimately the problem which stopped their research being successful. I think we have another question coming.
Yeah, I think we have another question from Gajananji. Yeah, you can ask.
Yeah, I am agreed with Dr. Richard. It is difficult to have cracking of the tar. Tar is a heavy hydrocarbon, but researchers are working. Thermal cracking and steam cracking may be the solution, but how it can be make it effective, it's a big question again. We are getting a good quality of the gas. We work in IIT Guwahati laboratories with Professor Pinakeshwar Mahanta sir, and we are successful to generate gas from the tar by thermal cracking. But if we are trying in case of the inline methodology in fixed bed gasifier or fluidized bed gasifier, it will be difficult because gasification requires the less temperature, while the thermal cracking requires at around 1100 degrees Celsius.
Exactly.
So then the gasification will not be possible. So how we can make it effective, though it will be a separate cracking unit. It may be the thermal cracking or steam cracking, but it's a big question, sir. How we can make it?
Absolutely. Yeah, as I say, it is that dilemma of what to do. You want the gas, but if you can't produce the gas at high temperatures. So I mean, it sounds very exciting. I mean, it may be just the case that it's one of the things which more research is required. To try to stop the tar molecules forming. Definitely more research is required. But it's very interesting here that you're processing the tar as well. I think that's really a good solution as well. So what we did at the factory, as I mentioned, was to sell the tar to local people to repair roads. So they were getting a small amount of money from that. But it still didn't solve the problem of producing tar in the first place. So more research. We need to work out a way to do this.
No, thank you, Dr. Richard. Thank you, Gajananji. Yeah, definitely there is a lot of more scope for research in this topic, and hopefully one day we all have our answers to it. Participants, if you have any other question, you have still some 2-3 minutes more time left if you can ask. Well, I guess there's no more question. Thank you, Dr. Richard, for joining us and accepting our request to attend this lecture. Thank you so much. I'll be in touch with you, definitely. And in the near future also, whenever we'll have this kind of endeavors, definitely we'll again approach you for sharing your knowledge with us as well as with the participants. Thank you so much for joining us.
Thank you very much. Yeah, so thank you very much, everybody, for attending. It's very good to see you all, and I wish you all good work, good success of your own research, and and I hope in the not too distant future to be visiting again. Hopefully, as research and allows and restrictions, and we get back to normal. So I very much look to seeing you all again in person and seeing your labs. Thank you very much, everybody, for coming along today. Much appreciated. Thank you.
Thank you so much, sir. Thank you.
Thank you. Bye-bye, everybody.
Bye. Well, participants, our last and the third